When making a loop method on the HT3, you will need to fill out values for each of these variables. When you click on the variable, it will give you a little summary of what each variable is and any maximum or minimums. In this video, we'll quickly speak through all of these variables and any recommendations we have for them. So let's get started. Constant heat time assures that each sample is heated equally. The constant heat mode allows for the highest throughput of samples as well as ensures all samples see the same thermal exposure time. It is recommended to add 5 minutes onto your GC runtime to get the constant heat time to avoid the GC system from coming out of sync with the Headspace sampler, as if the GC is not ready in the time the HT3 Headspace will error and abort the constant heat time, potentially resulting in several vials being exposed to too much thermal exposure time and the remaining vials being completed with poor sample throughput. GC cycle time. The total GC runtime including cooldown, so the total time it takes the GC to go from ready back to ready, i.e. from the time a run is started until the GC becomes ready for the next run. It is used for constant heat time calculation as the GC cycle time is used to calculate when to drop the next vial. Ensure you take into account the room temperature as this will affect the GC cooldown time. Valve oven temp. This is a temperature setting for the 8-port valve and the sample loop. The recommended starting points for the valve oven temperature is 0 to 5 degrees above the sample equilibration temperature. Transfer line temperature. This is the temperature for the heated transfer line from the Headspace sampler to the GC. It is recommended to set this temperature the same or 5 degrees above the valve oven temperature. Standby flow rate. Standby flow is the flow that is swept through the system to clean the lines and needle between samples to prevent cross-contamination. To quickly determine this flow rate, divide 1000 ml by the GC cycle time. The result is the starting flow rate that should be used for the standby flow rate. If cross-contamination is observed, it is recommended to first increase this flow rate. If problems persist, investigate high valve and transfer line temperatures. Platinum sample temp. This is the temperature the sample will be heated to allow the sample to reach equilibrium prior to sampling. It is not recommended to exceed temperatures above 15 degrees below the boiling point of the matrix. For example, if your matrix is water, then it is not recommended to go above 85 degrees. Platinum temp equilibration time. This is the time the platinum waits at the set point to reach thermal equilibrium before analysis starts. This only occurs on the first sample of a method. The main functionality of this variable is when there is multiple platinum temperatures being used within a schedule or when the unit is being powered up to run. If the same platinum temperature is always being used, then this time can be set to 0.5 to 1 minute, but if the platinum changes for the method, then it is recommended to set this in the 10 to 20 minute range. Please note that if platinum temperature is going to change throughout your schedule, then it is advised to start at the lowest temperature and increase to the highest as the platinum heats more quickly than it cools, so this will lead to more efficient analysis. Sample equilibration time. This is the time needed to heat the sample for headspace equilibrium. The sample equilibration time can easily be determined using the MOM function, which is explained in one of our other software videos. Mixer. This is the sample mixing prior to sampling. Mixing the sample typically helps reduce the heating time to allow the sample to reach equilibrium. Mixing level. This value corresponds to the speed that the mixer will turn. A power level of 1 is the slowest mixing speed and 10 is the fastest. The sample should never be mixed hard enough to allow the sample to be splashed onto the septa. Mixing time. The amount of time the sample is mixed. Mixer stabilization time. The amount of time the sample waits after mixing before proceeding to allow a sample to re-equilibrate prior to sampling. This parameter is typically set between 30 seconds to 2 minutes. Pressurize. The amount of gas added to the vial to ensure loop fill flow. The vial needs to have enough pressure to allow it to adequately and repetitively fill the sample loop. This pressure will normally range from 0.5 to 11 psi depending on the sample. Vial pressurization should be selected as 2 to 4 psi above the static vial pressure. Pressurization time. The amount of time the mass flow controller uses to reach pressurization setting. If the pressure setting is reached prior to the pressurization time, the unit will step to the next mode. If the pressure setting is not reached within the pressurization time, the unit will step to the next mode upon completion of the pressurization time. Pressure equilibration time. This time allows for the gas added during the pressurization step to mix and equilibrate within the vial prior to sampling. Loop fill pressure. The amount of pressure decay through the sample loop to vent. A pressure setting is applied to the loop fill mode, which controls the pressure within the loop prior to transfer to the GC. The higher pressures in the loop result in more mass in the loop. This directly affects sensitivity as well as eliminates variation in atmospheric pressure. Typically, a loop fill pressure is selected that is 2 to 3 psi below the vial pressurization setting for a 1 ml standard loop. Loop fill time. This is the amount of time required to allow the vial pressure to vent through loop. Gas is allowed to exit from the vial through the loop and therefore fills the sample loop with the sample gas for injection onto the column. Injection time. This is the amount of time the 8-port valve is rotated, allowing carrier gas to sweep through the loop and deposit compounds onto the column. There are two critical factors when setting this time, and that is GC carrier flow rate and the loop size. It is recommended that a minimum volume of 3 times the loop size should be flushed through the sample loop during injection to completely transfer the sample gas to the GC. To calculate this time, take the loop volume and multiply it by 3 and divide by the carrier flow rate. The standard loop in our systems is 1 mil, but SCION instrument offers loops from 0.1 mil to 5 mil, so ensure you know what your system has. If you wish to know how to make a method, please see our other videos.